Hey everybody, I had a request for some work on a problem where an object is being pushed or dragged across the floor and how to set that up. I thought I'd take this opportunity to get an example that includes some of the kinematic stuff that we learned in the previous unit as well. So in this one we're going to be loading up a shopping cart with, I don't know, a bunch of cat litter or something and pushing it down the aisle. We've got a constant force being applied to it. We've also got a constant frictional force. And the question is not about forces, but about a distance. Now remember, the only variable, the only value that appears in both the kinematic stuff and in the forces stuff is acceleration. So that's always going to be our bridge. I'm given information about forces, I'm going to use that to figure out acceleration, and then I use acceleration with the kinematic stuff to go from there. Every time I have a problem involving forces, first step is going to be to draw a free body diagram. So my free body diagram will start off with the dot representing the object. We've got a few forces acting on it. We've got gravity downward. We've got the normal force upward. We've got a force being applied down at this 25-degree angle here. And we've got a frictional force. At this point on the AP exam, you'll probably want to just go ahead and copy your free body diagram into a new space where you can make it kind of a working free body diagram. Remember, they like to have a pretty one with just the forces and directions labeled. So I'll go ahead and do that as my next step. On my working diagram, I like to go ahead and break up these diagonal forces into their x and y components, and I can go ahead and do some trig around those. Now, if we think about this situation, that shopping cart is going to stay on the floor. Presumably, it's not going to shoot into the sky or fall through the floor. So we don't really need to worry about the vertical parts of these forces. They're going to take care of themselves. They'll balance out on their own. What we're really concerned with is the horizontal parts of these forces. That's the acceleration that we're talking about, is a horizontal acceleration. So that's the forces that we need to look at as well. So I want to get a number for this x component of that pushing force. I already have a number for this frictional force, and that'll give me an idea of what the overall, or let me figure out what the overall force in the x direction is. So I'm just going to do a little trig to figure out that x component of the push force now. And by using cosine of 25 equals the adjacent side over the hypotenuse, I can figure out that the x component of that force is 45.3 newtons. Now I know both forces in the x direction, so my total force in the x direction I can figure out then is, I've got 40 to the left, so I'll treat that as a negative 40 newtons, plus 45.3 to the right, and I end up with a net force of 5.3 newtons. Now, I talked about this a little bit at the beginning. The bridge between our force information and our kinematics information is acceleration. So I need to figure out what acceleration is. And I know that's going to be equal to the net force, in this case the x direction for acceleration and force, divided by the mass. Here our net force is 5.3 newtons. And the mass, back to our problem statement, was 65 kilograms. And so we get an acceleration then of 0.082 meters per second squared. Now we have a kinematics problem where we know the acceleration, we know it starts from rest, and we know it's going to be pushed for some amount of time. I find it useful at this point to go ahead and write out just the kinematics things that I know. That helps me pick out an equation to use. So I know acceleration is 0.082 meters per second squared. I know my initial velocity is 0. Back to the problem statement here, I also have the time that it's pushed is 3.0 seconds. And since we're looking for a distance, let's go ahead and call that starting position 0 and say we're looking for the ending position. Now, looking at my equation sheet for AP Physics, there's only one equation that has the right combination of variables here, and that would be x equals x naught plus v naught t plus 1/2 at squared And that x naught is 0, v naught is 0, so v naught times t is 0, plus 1/2 times 0.082 meters per second squared times the time, which is 3 seconds squared. And so we get an answer here of 0.37 meters. So after 3 seconds of pushing, we're only about a foot farther than where we started here, which makes sense if we've got a pretty heavy cart. Probably time to push a little bit harder there, but we've got 0.37 meters for our final answer on this one. Thanks for watching. If you learned something from this, be sure to like this video, ask questions in the comments section, and if you want to see more videos like this, go ahead and click the subscribe button. Thanks again.